Hello, today we're going to talk about intermolecular forces. So intermolecular forces are different from intramolecular forces. In the last unit we learned about intramolecular forces like ionic bonds, covalent bonds, metallic bonds. Those are intra because they're within the molecule or within the compound, depending on the situation. Intermolecular forces are between compounds. So intermolecular forces would be if you had two separate molecules. Let's just use water as a simple example for now. And if that is interacting with another water molecule, this would be the intermolecular force. These solid lines would indicate it's an intramolecular force, in this case covalent bonds. But we use dashed lines or dotted lines to represent intermolecular forces. Now, sometimes the line gets a little bit blurry when we're talking about ionic and metallic because when something melts or boils, in an ionic or metallic compound, it's the intramolecular forces that are breaking. Or in a network covalent, which we'll talk about in the next unit, or in the next section. But when a molecular compound, covalently bound compound, when that is going to melt or boil, it's the intermolecular forces that break, but not the intramolecular forces that break. So it winds up being, kind of a little bit of a blurred line there, but make sure that you're focusing on whether it's ionic, covalent, metallic first, and then from there you can look at what forces are being broken when something melts or boils. So we're going to talk about 4 different types of intermolecular forces today. The first one is London dispersion forces. So I want you to picture a whole molecule as its own little blob. All right. So if you're thinking about like a water molecule, that would be the blob. Okay. So whatever the molecule is just within that blob. Now, at any given time, the electrons present in that molecule could wind up on one side of the blob. Right? Now, electrons are moving rapidly and randomly all the way around the molecule, so they're, randomly going to wind up on one side occasionally. All right. So that would be like what we call a random dipole. Random dipole, where once in a while it forms polar sides, a negative side and a positive side. Because if all the electrons are on one side, the other side must be slightly positive, slightly negative. Now when that happens, if you have another molecule, another blob, if there's all of these electrons on one side, it will repel the electrons in the other blob. And so they'll wind up on the opposite side. And you'll wind up with a slightly positive side, slightly negative side. And this is what we call an induced dipole. Because this one became polar, opposite charged ends, because of the random dipole in a different molecule. Now when this happens, now we have a positive side and a negative side. That's forming a slight attraction there, and that's called a dispersion force. So it's caused by the random motion of electrons causing these induced dipole forces. So that's a London dispersion force. Now, if the electrons randomly move away, then the London dispersion force breaks pretty readily. So dispersion forces are always like forming and breaking and forming and breaking in different amounts, different ways. They're definitely the weakest as a general rule. Unless you get these like really, really big molecules. When you have very, very large molecules, there's a lot more electrons present. So you're more likely to wind up with a charge distribution that is slightly uneven the more electrons you get. So we call that polarizability. Larger molecules have more electrons, and so they are more polarizable. if it's more polarizable, then it's more likely to form those random dipole moments and then induced dipole moments, so it will have stronger London dispersion forces. The next type of intermolecular force is called a dipole-dipole interaction. Dipole-dipole interaction is for things that have a permanent dipole. On the previous slide, we talked about London dispersion, which have those random dipoles and induced dipoles, but those are fleeting and based on the random motion of electrons. Every molecule can have dispersion forces. It's just the bigger ones have stronger dispersion forces. Dipole-dipole interactions, on the other hand, is very specifically for polar molecules. Things that have a permanent dipole. And essentially, these are synonyms. Polar molecules have a permanent dipole. They have a permanent charge distribution. So let's think of something like NCl3. Okay, so NCl3 is a trigonal pyramidal molecule. It has a permanent dipole because of this lone pair here. So it's going to have that uneven charge distribution. So that would be, it would have a permanent dipole. Let me draw another one. This one may be a little simpler to see. Let's do HBr. So HBr, like this, has two ends, one that is negative, slightly positive, and one that is slightly negative. And that's always true, because that bromine always has more electrons around it, the hydrogen has fewer electrons around it, so it always has that uneven charge distribution, a permanent dipole. Now, if I were to draw another HBr molecule, another blob there, right? This hydrogen has a slightly positive end, and this bromine has a slightly negative end. Because of the permanent dipole, we can form what's called a dipole-dipole interaction between the bromine and the hydrogen. And this one is not fleeting like the London dispersion forces. They're going to line up in a particular way. The molecules are going to line up in a particular way so that the negative charges line up with the positive charges to form those interactions. And so that's a dipole-dipole interaction. It's typically much stronger than a London dispersion force. The only kind of scenario where you would see London dispersion being stronger is if you have a very, very large molecule where that's really polarizable. Those London dispersion forces could be stronger than a dipole-dipole interaction. But usually they'll have to give you information to help you support that. So like they'll say the boiling point or the melting point is lower in the polar molecule than it is in the non-polar molecule. If the boiling point is lower, then you know the intermolecular forces are weaker. So they'd have to give you some kind of information so that you would know the dipole-dipole interactions are weaker than the London dispersion forces. If they don't give you any information, assume that it's the reverse. Dipole-dipole is stronger than London dispersion most of the time. In terms of comparing the dipole-dipole interactions among polar molecules, if it's more polar or more uneven charge distribution, it will have stronger dipole-dipole interactions. We can measure this in what we call a dipole moment. You don't know you don't need to know how they measure the dipole moment, but just the larger the number for dipole moment, the more polar it is, and so the stronger dipole-dipole interactions it will have. Okay, hydrogen bonding. Hydrogen bonding is just like a special type of dipole-dipole interaction. It's extra strong, right? It's when you have hydrogen directly attached to oxygen, to nitrogen, or to fluorine. So those three elements, you must have this, and notice I drew a solid line, so those are covalent bonds. If you have those covalent bonds, then the hydrogen can form a hydrogen bond with another thing. And that's because oxygen, nitrogen, and fluorine are the most electronegative atoms. Because they're so electronegative, they pull the electrons in each of those bonds much closer to themselves. And so the hydrogen doesn't have the electrons for as often, basically, because it's an uneven sharing of electrons. So the hydrogen winds up slightly positive, but more so than in other compounds. All of these will wind up more slightly negative. And so let's look at water. When you have a water molecule, that hydrogen can form a hydrogen bond with another water molecule, for example, because this is slightly positive and the oxygen is slightly negative. You could also, instead of having to bond with another water molecule, it could form a hydrogen bond with something else that has a lone pair, like if you have formaldehyde here. That hydrogen could bind to the lone pair, form a hydrogen bond to the lone pair on the oxygen in formaldehyde. But these hydrogens cannot form hydrogen bonds because they're not directly attached to oxygen, nitrogen, or fluorine. So it's only the hydrogens that are directly bound to those three elements. I remember it as hydrogen bonding as FON, like fun, but it's spelled weird. So fluorine, oxygen, nitrogen. And let's see. Anytime you have something with one of those bonds present, it can form hydrogen bonds with something else. Let me give you another example. Alcohols can form hydrogen bonds. So like this is methanol. And so this hydrogen can form hydrogen bonds with another compound. Another common one is ammonia, NH3. Those hydrogens can form hydrogen bonds. Hydrogen fluoride can form hydrogen bonds with other compounds. They can form hydrogen bonds with each other. So like you could form a hydrogen bond there. So there's lots of options there, but basically it's just a much stronger dipole-dipole force because of the high electronegativity of oxygen, nitrogen, and fluorine. But all the other rules apply. Dipole moments certainly help increase the strength there. But hydrogen bonds tend to be the strongest, so they're going to have higher boiling points, melting points, just stronger attraction, so it will be harder to break. Okay, the last type of intermolecular force is called an ion-dipole interaction. As the name suggests, you must have an ion and a dipole, or a polar molecule, present. I'm going to use water because it's the one that comes up the most often for this, but it could be any polar molecule. So you have a slightly positive side and a slightly negative side of your polar molecule. The positive side could interact with a negatively charged ion. So notice that this is a full negative charge, whereas this is only a partial positive charge. So this is the ion, and this is the dipole. So this interaction is called an ion-dipole. The negative side could interact with a positively charged ion, and that's why ionic compounds can dissolve typically in water, because water is a permanent dipole. It can form ion-dipole interactions with the ions in an ionic compound. Okay, I want to take just a minute to mention like really large biomolecules, things like DNA and proteins and lipids. Essentially, if you have a really large molecule with a lot of carbons, a lot of carbon atoms, you're going to see lots of London dispersion forces. And the larger it is, the more polarizable it is because there's more electrons, so the stronger those London dispersion forces. For really large molecules, so this is generally what's going to have the greatest effect. You should also be on the lookout for OHs. Sometimes they'll just draw it like this, OH, but that is directly bound, so that can form hydrogen bonds. Like the two strands of a DNA molecule are held together by hydrogen bonds between the nitrogenous bases. But yeah, so London dispersion, be on the lookout for hydrogen bonding, and you should be set. Okay, so let's say we have C5H12, and we have C8H18. There's pentane and octane. They're two alkanes, so they're hydrocarbons. There's carbon and hydrogen. What type of intermolecular forces are present? Well, anytime you see just all those large amount of carbons and hydrogens, it's going to be, they're nonpolar, both of them, and they're going to have London dispersion forces because they're nonpolar. Now, if I were to compare the two, which one will have the stronger London dispersion forces? It's going to be the larger molecule, because the octane is more polarizable. It has more electrons, so they're more likely to form that random dipole and induce dipoles in other molecules to form those London dispersion forces. So octane will have the higher melting point, octane will have the higher boiling point because of its larger size. Okay, let's say we have two molecules. Let's say we have HF and F2. HF has a boiling point of 293 Kelvin, whereas F2 has a boiling point of 85 Kelvin. Why is there such a discrepancy in their boiling points? Well, the best way to figure this out is to determine their intermolecular forces. Now, F2 is a nonpolar molecule, so it will only have dispersion forces. HF, on the other hand, it will have London dispersion forces because everything has dispersion forces. It is also a polar molecule, so it will have dipole-dipole interactions, and it's FON. Hydrogen bonding is FON, right? So it has that H directly bound to the F, so it will also have hydrogen bonds. So the reason why HF has such a higher boiling point is because it has much stronger intermolecular forces. It has the dipole-dipole forces and the hydrogen bonds, requiring more energy to break those in order to become a gas. F2, on the other hand, has just the dispersion forces. They're weaker. It requires less energy, so it gives it a much lower boiling point.